there's a couple things that we want to focus on. The first being, I was using a different approach the other day for this. I'm going to start with it this way because of some of the detail that we have here. And I'm going to make it with a few different rectangles. I'll zoom in a little bit so you guys have a little bit better view of what's going on here. And then another rectangle here. So could have done this with lines, could have done this with lots of different things, lots of different approaches that I could take to this. This, I want to delete the parts that I'm not holding on to. And in this case, I want this U shape left with whatever I'm doing. Why do you guys think we want to pay attention to how efficient we can be with the maximum number of features for the minimum number of sketches? Which one takes more time? That's the first thing. Tell me in the chat, which one takes more time? Is it the features or the sketches? And then before I set the smart dimensions, another thing that we have to note is on this particular one, they give us the warning that everything is done with the IPS. So for this one, it's on the right plane is where I started this. But for dimensions, you want to use this drop down in the bottom right to be able to switch back and forth. They give us the IPS as the scale for this one. So that's what I have selected. And zoom makes some of this fun stuff disappear. Note when you change that length scale for things, hopefully you guys have seen that before. When you change that length scale, it's going to kick you out of whatever sketch you were in. So you got to step back into it and continue editing. So this in total is 2.7 inches. That will reset kind of the scale of things, make life a little bit easier. Smart dimensions, here we go. You're going to have to go back and forth with the tools and do a lot of little detail work. So this is 1/2 inch. This. Now here's the real question. Based on the dimensions given in the drawing, can you guys figure out what the thickness of this plate is? Somebody drop it in the chat for me. There's an obvious answer, but we all know that the obvious answer is usually obviously wrong. So somebody see if you can identify from the PDF what this actual thickness needs to be. The doc should be attached to, it should be a PDF that's attached to the announcement. I should be able to drop it here as well, so long as Zoom cooperates, which is not really an ironclad guarantee. So let me pull that up real quick. All right, so you should also have it in the chat. I can't be held responsible for shortcomings of a particular glorified learning management system. I'll let you do the math on which one that is. It should be in this week's announcement. However, posting things is very, very difficult. So once you open that exam assembly practice, take a look at the drawing and tell me what you think the thickness needs to be, because that turns out to be very important.
Is it 0.1?
So 0.1 inch would be the obvious answer. Let's take a look at that real quick and see. So 0.1 inch. Let's just say, for instance, that's our thickness. If we then extrude this closed region by the 6 inches, the 6 inches, not 0.1. Keyboard's having trouble registering today. So if we were to take a look at that as an example, hopefully you guys have learned all the screen manipulations by now, especially that control click the scroll wheel trick. Hopefully you're all running mouses and mices and mices as well. Those are very, very important for SolidWorks. Trying to do this on a trackpad will drive you pathologically insane. Does this aspect ratio look right for our part?
After you extruded it, how did you create that symmetry?
So the symmetry here is just from the base sketch that we're editing. And since I don't know exactly all the details you guys have covered in class yet, I'm not going to just assume and kind of rip through all the parts. So this is what our sketch looks like. But that aspect ratio is not quite correct because the difference in overall thickness, I'll do it up here so that it's a little bit more clear what's going on. So we know this is 2.7. We know this interior is 2.6. I was only off by 0.010 of an inch. I just want the record to show. And right now, this is a non-uniform thickness on either side. So the point that we have to drive home here is this. It actually becomes a thickness of 0.05 inch because you need 2 of those to get between the 2.6 and 2.7, right? So it's half the distance of the difference in between those. So 2.7 minus 2.6 divided by 2 is 0.05. And that's our thickness on this part. So this part wall also needs to be 0.05, not 0.1. And then if we hit the check mark, we step out of the smart dimension, we step out of the sketch, and we have our base for this plate, right? So in a single sketch, we captured a good 3/4 of the important detail and key dimensions of this part because we're trying to take advantage of the symmetry of the part, right? Because you could spend probably 20 minutes or at least a good 10 minutes extruding a rectangle on the bottom, then making a plane on this side, and then doing a sketch and extruding it, and then doing a plane on this side, and then doing a sketch, and then extruding it. Or you could leverage your symmetry, and I will open up as an example, because I did that with the part yesterday. Which one? I want to say that was 2, maybe. Let's see if I remember right. Yeah. So this one, as soon as it finishes loading, we'll do, come on, load the model. This is interesting. Let's see. All right. So this should be actually opening the part. That's very interesting. Why did it not open the actual part? Here we go. Okay, there we go. So this is what I was trying to show you, the part detail. So this is part of the reason why the part tree is so important. Hopefully Dr. K has gotten a chance to speak to all of you about it. So the default is often to take an approach like this. You extrude a rectangle, then you make a plane, and you make a sketch on that plane, and then you extrude. Now, in this case, I leveraged the same sketch to do an extrude and did different parameters. So I'll show you what both of those look like. And this is a perfectly valid approach. It just takes more time than it absolutely needs to. So you start from the sketch plane, do a blind extrusion, because I extruded it from the very edge of this face and extruded it in by 0.05 inches. Then on the other side, I used the same sketch, but extruded it going the opposite direction from this face. So one sketch, two different extrusions, right? This is another approach that you can take, or you can manually redo the sketch. Sketching takes a ton of time. It depends what's the most time efficient, but often what you'll find is the approach that I'm showing you is what I recommend, because that's going to leverage the symmetry of the part the most. So the time and everything like that won't necessarily be to scale, but there are a few things that you can capture very, very quickly, one of which is this fillet. So it helps to kind of zoom in and find all of your individual edges. It helps to zoom in and find your individual edges. These need to be a 0.25 radius. And then the second fillet, based on the information in the drawing, is going to be these two interior edges, but these are a 0.025. So they're a very small fillet. So now we've captured all of our fillets, right? So we've done a similar number of operations compared to the other method. But here I did most of the detail and then just did a final fillet. So instead of doing a fillet on the already extruded part, this was done on the actual sketch itself. So I did sketch fillets, which is this tool. Hopefully you guys have seen how to use those. So there's a few different ways that you can go about it. This one just happens to be the most time efficient. So now what you can do is, with a single operation, you can add a sketch to that surface. No, not edit the sketch. I want you to do what I say. Sometimes you'll have to start a new sketch. Sometimes SolidWorks will do interesting things. So you have to step out of a tool using the escape key, step back into it. So here we're going to need just a couple circles. These are going to be pretty easy. 0.25 inch diameter. And they're going to be on what's called a 1/4 inch pitch. So 0.25 inch and 0.25 inch. So pitch has to do with the spacing of holes. You can either index based on the bottom edge, or really help to zoom in. You want to pick that flat edge. All right. And your radius. So diameter of 0.25. All right. So now we can simply do one quick extrude cut. We already have that sketch highlighted. You're going to switch from a blind to a through all both, which is cheating. And that part's done. So the only other thing that you would need to do is specify, I think this one is an AISI 1020. So we'll go ahead and specify material. Yep, AISI 1020. Apply that. All right. So now we have our material applied. The material is going to make a huge difference. I know Dr. K has already focused on that with you guys, so we won't spend a whole lot more time. So I'll pause here for a second and see what some of the questions are. That way I can get some feedback and address any convert. So there's two different approaches that we can take to this. One is going to be really, really fast, and one is going to be really, really slow. So for this one, we use the technique of this base sketch and extruding. For the next one, we can show what it looks like to use multiple solid extrusions. It just takes a lot longer. The quick and dirty method of being able to recreate this is so in this case, I'm going to save this as, this one is 2B. Because I know something about that part numbering scheme. Not really important why. What you want to do is look critically at the drawing, and if you have two parts that are very similar, in this case, 1/4 inch pitch, meaning 1/4 inch from the edge, same radii, same diameter holes, same part thickness, same fillet radius. If all of those kinds of features are conserved, rather than recreate this in a new sketch, the simplest method is to go in and redefine the base sketch that we used for the symmetry. And this is part about thinking sort of what Back to the Future referred to as fourth dimensionally. This is actually thinking fourth dimensionally, but in a real sense. So you go back to the base, you edit the one sketch, and instead of 2.6, this becomes 2.4. And instead of 2.7, this becomes 2.5. And now we exit the sketch. And we step out of that tool. And now we've recreated our new part. And now we're done with that part. So we save that as part 2C. So this is the smaller version. We'll see where that matters coming in. The natural approach for a lot of you is probably going to be something like this, where you're going to create a first sketch. You're going to think, okay, top plane, I'm going to recreate this. So you can do it this way and say, okay, if we're recreating this smaller of the two parts, move this off so that I can see what my key dimensions are. Let me change view real quick. There we go. So this one here again, I'm going to have to change, because we have to pay attention to whether or not the drawing is set up in IPS or MMGS. Most of the CSWA exam parts will be MMGS. So it's something you want to keep in mind. You can always manually enter 22.5 millimeters, even if it's in MMGS, or even if it's an IPS and not MMGS, you can still work in the dimensions. It just is more headache, more stuff you got to track. So 2.5 is the outer dimensions, 2.5 inches and then step back into the smart dimensions, 6 inches length. Now, another way that you can recreate most of the geometry without doing extra work is to think, I know I'm going to have to extrude these. And instead of thinking about extruding them from the side, we're going to use the same base sketch to capture as much of that detail as possible. So this is going to be our same 0.05 inch thickness. This is going to be our same 0.05 thickness. So we now have a fully defined sketch. Okay, the base is done. The reason I've done it that way is I know I'm going to use this sketch. I'm going to zoom in to select all 3 of these regions. Or you could do it if you just wanted to do 2 operations because of the different thickness. You could do it this way and say, I want to do the interior region, 0.05, and then say, I want to do another extrusion. You want to leverage that same sketch so you don't have to go in and recreate dimensions 6, 8, and 32 times. And you know those 2 features are going to be the same. You always want to deselect the thin feature because the thin feature always ruins your life. Thin feature typically tells you that you have a non-closed sketch or an open looped volume. So I'm going to delete this contour because that creates confusion. A lot of times I'm in the habit of clearing the selected contours so that I know exactly what it is that I'm selecting. I like to just have that level of control over the operation that I'm doing. And you extrude this to 0.5 inch. So similarly, I don't lose a lot of time using this technique because I know I'm going to do these 2 extrusions. But compared to doing the same sketch on the side plane and then doing an extrusion, then recreating the sketch on this side and doing another extrusion, I'm trying to always think in terms of how do I approach the geometry and do as few sketches as possible to get the most level of detail possible out of the part. So this is just the way that I've come to think about how I approach parts. And it served me really, really, really well in SolidWorks. So I'm trying to impart that to you. I know Dr. K has some similar ideas, but he teaches a little bit differently sometimes in the approach. So this is hopefully stuff that will just get you guys to think about the parts themselves. So now we come in, do the same thing with our fillets, but I want to deselect that face. I always want to be controlling what faces or facets are being filleted. So I'm constantly zooming in and out, constantly moving parts around because I need control over what the operations are. Nope, not that face. Sometimes the mouse is there to help you. All right. So 0.25 inch radius. All right. So we've got the majority, and then we just need the same things. We need to add a sketch, and we can click a face of something. We don't always have to use a reference plane. I'm in the habit of using reference planes often. That's why I have this reference toolbar available on my left side. So if you guys haven't seen that, make use of this view menu under toolbars and select ones that you're going to use all the time. Reference geometries for me are key for a lot of things. I'm not doing mold making and other things very often. So the reference geometries, that just happens to be very accessible because that's probably really a thing that should be here. It's more easily accessible in the sketches, but a lot of times you in the assembly operations and things, but you need it often in the sketches as well as you're working. So yeah, there's a reason why it's in the features panel instead. We won't go into that now, but this one I'm going to go ahead and draw on the side just to be quick and efficient. So same deal, 0.25, then set up the 0.25 pitch. Same thing here. And you can even make better use of some other features, like for instance, if I didn't want to do that, I'm going to step out of the tool there. I'm going to delete this. Yes, universe won't actually explode. If there's a lot of features, then what I'm going to do is I'll step out of that sketch. I'll make a reference plane, but I'll do it in this way, where I'm going to pick the actual points, not an edge, but I'm going to pick the actual center point. I'm going to pick the center point here. And then I'm going to pick the center point here. And that usually gives me, even if I use this one, there we go. 3 points defines a plane. What I can do is use that plane as a bisector if I'm working on a part that has symmetry side to side. There's a couple ways you can do it. So again, just trying to get you guys to think about some of the different options. We can go back in and edit this sketch, or we could edit this sketch and we could say, maybe I want to go ahead and do that extrude cut. And I'm going to say through all. And then I say, now I want to take that and I want to mirror this. You can mirror this about the plane. And what you'll see is that same operation can be copied over. So there's a lot of ways to leverage the symmetry in the software that you can do some very interesting things with. You just have to think in terms of how can I get the most effect out of the process. So doing the 3 different sketches and multiple extrusions and extrude cuts is the longest possible way to make the part and is going to consume the most time. So different approach, still using some of the time-saving techniques in terms of thinking about how to leverage symmetry in the process. Really, I could have just designed 1/4 of the whole thing and done a lot of mirroring to get to the end result. But where that's going to bite you is if the part then is told to change. It's one of the things that they'll do, especially in the CSWA, is they'll make you do something and they'll do a part 2 of that question and they'll change these values on you. So suddenly maybe the length here at B is different in the new version. And then they change the angle for C, and then maybe the diameter of this changes. If you used symmetry for absolutely everything, sometimes they'll make changes that'll make it asymmetrical. And if you use too much of that and try and be too clever, you can end up having to recreate the part again anyway, or modify the final version. There's still ways around it, but it's things to be thinking about and considering. All right. So the next group of parts, the cylinder for the center is pretty simple, but let's focus in on the pins and why it's so important to be able to use the symmetry that's involved. So before we do that, any additional questions? When we go to create the pins here, there's a couple things that we want to keep in mind. One is, because these are cylindrical, there's symmetry. So let's take a vote. What approach do you guys think we should be using based on the kind of geometry that's here? What approach should we start using for this? Should we do extrudes? Should we do extrudes and domes? What would be the most efficient?
I think someone said revolve in the chat.
Yeah, revolve. I was looking to see if anybody else was going to chime in or if everyone thinks it's a trap. The answer is it's always a trap. So what we're going to do is use our vertical reference here. We're going to switch again, since everything in this particular part has to be IPS. And we're going to create, I'm going to go back to this sketch. Here we go. And we're going to create this part of it. So really, this doesn't take a significant amount of time, but it's something that we want to be thinking about. And in the case of the part that we're making here, I want to make sure you actually get the concentric point. There we go. So you want to make sure that that bullseye looking symbol actually gets highlighted. Bunch of reasons why. So there, my base geometry is done. Why? It's not dimensioned yet. So I'll go ahead and do this just so that we can see why we want to do this. We only want to mirror it on the one side. And then we can dimension it after the fact. So we have two different sizes. 2.9 and 2.7. You can also cheat. Sometimes this will make a mess of things, not always. Radius of 0.225. Um, this one, I think that's actually a typo on that one. Yeah, that one's actually a typo. The overall thickness of this is 0.25. So let's go ahead and set the dimensions here, because this turns out to be very, very important. So at 0.5, this is 0.125. So this (225) because of the center point. I'm going to delete this relation for a moment. The relation between that center point on that line and our center line created an issue because reasons. So then our overall distance is going to be a little bit less. That actually, yeah, this is our center line. So that part's correct. So center line, and this one. So just for the sake of interest, you can specify this dimension. Doesn't really help because the distance we really need is this one. And at 0.145, this becomes very important. So let me take away a couple of these dimensions and we'll see why it becomes so important. If we don't have a fully defined sketch, some of the things that can happen. So we're going to revolve this region about that axis, and you want to turn off the thin feature because that ruins everything that's important, and you have a pin. So now you can save this as a part. So I'm going to save this as this one. Save as LP. Then we're going to take a look. So LP stands for long pin. SP will be for short pin. So here again, instead of going in and recreating the geometry, it's often going to be easier to use 2.7. But I'll do a slightly different thing with the dimension so that you can see what happens. So we know 0.225 and 2.7 gives us the overall length. So it's the effective diameter created by this. So 0.55 and 2.7. So I'm going to change the overall length of this pin in order to save it as the small pin. So that's going to be SP. And then I'm going to go back to that base sketch. So this overall length, you can do it here as well. But this is going to be based on our dimensions here, 0.27 plus 0.55. Just still have that dialog box open. 2.7 plus 0.55. $3.25. So now we step out, rebuild it. Anyone see a problem with that? See if any of you spotted it. The long pin and the short pin. Did you guys catch the problem? My overall length is right. That overhang is the same. Because the sketch isn't fully defined, what happened? Let's take a little closer look. Hmm. 0.8. It's actually 0.075. What should it be? This is why the fully defined sketches matter, especially when you go to make changes later. So it should be 0.125, right? Because 0.25 over 2 is 1/8 of an inch. So 0.075 is way off because we just changed the length of the pin overall. So by messing around with the arc and that distance, I knew it was going to mess it up. So I wanted to show that to you guys intentionally so that you could see what was going on. Now you can fix that easily enough by commanding it to just be 1.25 as it ought to be. Now we have the short pin. But we want to double check and make sure that we know where our radius is, because where's the radius of that arc? So is that arc right? It's the wrong value for our radius. What should it be? 0.225. Wow. So stuff gets really messed up when you don't have a fully defined sketch. It's almost like we tell you that for a reason. So I wanted it to fail in multiple ways so that you could see just how far off you can get, even though it seems like it might still be kind of correct, right? So we want to pay attention to all those little details when we go to put together parts for anything in the CSWA. So we're going to save that. Make sure whatever garbage we had originally was completely erased. All right. Next part. This bar is pretty straightforward. You're just going to need a lot of them. So for this one, what do you guys think? What's the most efficient way to do this one? Let's take a vote in the chat. Yeah. This one's going to be far more efficient from an extrude. So it's the right approach to be thinking. All right. But instead of thinking in terms of extrude and extrude cut, you want to think in terms of how much symmetry, again, can I leverage? Look, man, it's just a rectangle with some end caps. Like, how hard is this? You'll see. I want to get you guys, again, thinking about symmetry. Symmetry is so, so, so important. Yeah. And I'm going to switch to IPS for each of them. All the warnings. All right. Circle. Going to go back into the sketch. There we go. Edit the circle. You can use the slot tool. Absolutely. It's not necessarily a whole lot more or less work. We'll put the slot down here just as a point of comparison. So you can use the slot tool, and that works very efficiently. No, I want a circle. Circle. This one is just a quick method of how to think about it. Otherwise, you're probably ending up with the slot centered at the origin. There's times when that's beneficial, times when it's not. So that one, in terms of time efficiency, pretty much comes down to personal preference. So this is 0.25. This one is 0.25. These radii, 0.25. That length is 6, center to center. So center to center, 6 inches. Now, the slot tool, I wanted to do this on purpose. The slot tool will not do this. Some of you get to this point and you're like, well, I'm going to fail the exam. But when something like that happens, you just want to think about, actually, let's take that distance down to 0. So quick recovery from what is really ultimately just a distraction. And that one should be fully defined. Five. Then this one didn't have full definition because it was missing some of that detail. So what I was doing is I was orienting this end of the sketch relative to the origin, because I recognized from experience that that's what detail it was missing. A lot of ways how you can tell that, and once you're done with these kinds of movement dimensions, you can typically get rid of them. What this is attempting to do, yeah. You have to establish some horizontal distance for the arc, because these are arcs. That's something that is built into relations in this slot tool differently. So getting a fully defined sketch is going to be just a few seconds faster in a slot. Just something to keep in mind. So normally you guys would see 3 different versions of a 6-inch length definition on a part and think that's going to be overdefined, but it's not, depending on how things are set up in the actual sketch itself. So now step out of that tool and delete this. I just wanted to show you again some different examples to get you thinking and to teach you how to recover when you start down a path and then kind of get stuck. So these actually do get extruded to 0.1 inch width. And again, you'll specify the material to AISI 1020. I think I didn't do that with the pins, but you'll get the idea. We'll go back and do that for some of these parts for the sake of completeness, because it turns out to be important. A couple more. Each time you update the material, you want to make sure that you save it, because that will update in the actual part itself. Recent long pin. There we go. ASI 1020, apply. Okay. Last part, I think, is our cylinder. So I'm going to use the right plane for that one. Switch to IPS, just because it'll make keeping track shorter, fewer things for me to type. So let's see, this one. Oh, there's the end callers. Yeah. Forgot about those. All right. We'll show maybe a couple different ways to approach those as well, and then get into the mates so that we can dig into how to establish some of those relationships. Because a number of them that we're using today, I can guarantee are going to be on the CSWA exam. So you want to pay very, very careful attention. This one, was it 0.375, I believe, and 0.55. Yeah, 0.375 and 0.55. It's almost like I've been here before. Now, there's a few different ways to approach this. We have our fully defined sketch. What's the easiest? Let me know in the chat. What is the easiest method of approaching this? What's going to get you the best results with the least amount of time? What do you guys think? So a revolve is close. There's a reason I did it this way. With a revolve, you're drawing a couple of rectangles, and it's going to be a pretty close to a dead heat. So we're not quite to the cube yet. This is actually this part right here. We're making this cylindrical rod that goes through the center. So we'll get to the cubes here in just a second. because I think the approach to those parts is going to surprise you guys. So we're making this cylindrical rod.
Would it be a loft?
You could use a loft to do it. Since there's not any kind of funky transition and there's only a couple steps, this is where you're actually going to get more quickly out of a pair of extrudes than you are really anything else. And because of the two different sizes, you have to do two operations no matter what. The revolve would be a single operation, so that also does fit my criteria. But we'll do it this way just to show, again, an example of how to think and how to approach these parts. So we know what that distance is, and it's 6.7 inches for B and then 20 inches for A, I think. 6.5 and 20.5. I was pretty close. All right, 6.5 and 20.5 are our two key dimensions. So do it from the sketch plane, but if you don't constrain yourself early on, you can take advantage of what's called the midplane, and you can say 6.5. Now, half of 6.5 is on one side, half of 6.5 is on the other. I do another extrude. So could a revolve here be slightly faster? Maybe. 2 circles is pretty quick. Select the contour. Just the inner. Select my material. And I'm done. I have a fully defined part. Right? So the midplane extrusion actually is very, very useful for that kind of part because we can leverage the symmetry that's involved a little bit more efficiently. So I do 2 operations from the same base sketch and I'm done. So this one, I'm going to save as 1B. All right, final part now. This one, we need 2 of these guys. So a couple different geometries involved. We've got to vote for the cube. What does everybody else vote? How would you create this part? The inside of that part, what I was doing was selecting the geometry. So I went back to my base sketch, and when I went to do this boss extrude, I cleared the contours so that I could just pick the region I want, and you can pick either of those regions. I just picked the inner region because that's the one I wanted. I could have done the same thing for the outer region and then done a completely hollow extrusion. Same technique works for a lot of other things, but the one that we actually want is that interior region for this part. There you go. Tyson's thinking correctly. So what we want to do is we want to leverage the part that we've already created because that's the correct way to approach this. So you can start by creating the block, creating the thing. If you don't have to recreate something 100% from scratch, don't, because it wastes time. It's not needed if you've already created something. So in this case, I need to work from the longer pin because that has the 0.25. So I'm going to save this as the last part before I go messing up this specific part file. There's ways to recover this, and I'll show you what that is as part of this process too. If you get just flat out too excited and you get too far along, we're going to do 4B for block. All right. We're going to take this. We've already got the majority of the things created here. We could go back and edit this base sketch. I'm going to not do that for this particular part because I'm going to create another sketch that is separate from this revolve. But I am going to create it. No, I don't want to edit the original sketch. I want to create a new sketch specifically. SolidWorks often reads my mind very incorrectly. Imagine that. Now I'm going to come in here and do a center point rectangle. Now I want you guys to be in the habit every time you go to do this operation. I want you to be in the habit of getting this, of resetting your view every time you go to look at a sketch so that you're working perpendicular. I still make mistakes sometimes if I'm doing a sketch off axis. I can do it, but it's not the most efficient. So you want to make sure you're keeping your view square to whatever you're working with because reasons. You don't want to end up costing yourself time and having to do work again and again and again for no good reason. So it's a 1-inch cube centered at the center point of the pin, which makes this fairly easy. This one, what's that diameter again? 375. Yep. All right. 375. Nope. Wrong part. 4B. Another reason why I chose this as a specific example is it gets to be a little hairy. There's a lot of individual parts to create, a lot of techniques to cover. It's a good refresher on drawings, etc. 375, so it's pretty close. All right, this is now a fully defined sketch. So we extrude. You want to make sure it's this region. This one, you're going to do mid-plane, 1 inch. And that's what it's going to give us, a mid-plane 1 inch, which you can take advantage of because of how this works. We still have to do our through cut. So we're going to do an extrude cut, use that same sketch. Wait for it to load, same region. Select that interior region, and you can do a through all. The problem is that's only going to cut the one side. So in this case, you need to do a through all both, and that will cut out your hole. Then all you're left to do is a chamfer. 45 degree at, I think this is a 0.05. Yeah, it looks right. There we go. And because we had already specified the material for this, it saves us a fair bit of additional looking through things. So if we can leverage an existing geometry to get the features, then we're going to be in good shape. So 0.05 inch chamfer at a 45 degree angle is what that notation is referring to. And I don't have to worry that the block is at the center point because I set the center point of that revolve as the same center point for my rectangle that I turned into a square. So saved a lot of work and additional headache to recreate the whole entire thing by leveraging the part that already exists. So these are some of the things that if you are familiar with that process, the CSWA will let you do. So it's just something to pay attention to. All right. Now we have all of our parts. We need to assemble them. So we're going to make an assembly. And then we're going to spend the next 150 years doing mates. So you might want to get it comfortable or stand up, do a little neck roll, get the blood back up into your brain, right? All right. We're going to do 1B, 2C, 3SP, and 4. I'm going to bring those in here at random. We're going to insert some more components. There's another thing I'll show you kind of quickly. 4B. So we've got a 4B. We've got 2C. We need a 2B. All right. So this covers most of it. What did I save this one as? 4. Yeah. I think I resaved this as 4. It's all right. Going back to the assembly, which is denoted if you're going back and forth between different things. It's denoted here. We're going to need part 4. Oh, nope. So this one, oh yeah, this is not saved yet. This was just a random part. So again, save early, save often. 5R. We're going to go back to the assembly. And we're going to bring in a 5R. Nope, we'll come back to linear component pattern. We need to bring in a 5R first. 5R, come on. There we go. All right. So these are all distinct parts. We're also going to need, we've got a short pin. We're going to need long pin as well. So grab one of those. Long pin. All right, that one needs updated. So let me go back and edit that one because that one did not have the material saved. LP. Easy little details to miss. There's another reason I picked this example. It's very pedantic. There's some repetition, but it's a very good example such that if you can do this and you can do it reliably, you can make it all work. So now when we go to the assembly, you'll see that our material has updated because it auto updates the assembly based on the saved parts. Now, you can do linear component patterns. The problem with this, you'll see in just a second. I need a total of 8 of these. And this is the entity that I'm using. And I need it in the direction of, I'm going to cheat here. Say I need it in the direction of, nope, delete. In the direction of, come on now. the direction of this face. The problem is when you do a pattern, they are all linked together, which if they should be, that's okay. You could bring these in as pairs, technically, because of what we're having to do here. Most of you are not going to think to do that. So I'll show you what it looks like to do a couple of pairs versus a couple of others. The problem is, especially with the way that they're linked, you need to be able to control the individual distances. So it's really best to add mates and constraints individually for these parts. Whole bunch of reasons why. So the first thing in is going to be what's called fixed. So you have an option to fix or float. I'm going to go ahead and float this because I know I'm going to be moving a bunch of stuff around. And instead, I'm going to take a look at what our instructions tell us is right here. Lower base is the wider one. And in our assembly, it becomes real obvious which one is the wider of the two. So because this is the lower base, what I'm going to do is I'm going to fix that component so that other stuff can move. I'm going to get rid of this local pattern because we really just need this one. The copy component option also really doesn't help you in the way that you might think. I seem to recall there was a move or copy option up here, but that appears to not be there anymore. So that may have been something they got rid of. And you'll see an option here that looks really enticing. Oh, just copy it with the mates and then everything will be great. Problem is you can't even select that part. So you can't select that component. So it doesn't really do you any good. All right. So real quick, we're going to bring in a couple more of these. So we're going to insert component. We're going to bring in some more 5R. And really, there's just not another way I'm familiar with on how to bring in 150 of something without it taking a couple minutes. So we have 1, 2, 3, 4, 5. And it just takes a little time. So now you have 4, 5, 6, 7, one more, and then all our 5Rs are in. Okay. So 4 and 4, got those. We need one more each, the long pin and the short pin. This is why naming them carefully turn out to be pretty important. So there's a short pin. Here's the long pin. All right. Long pin, short pin, and we need one more block. A lot of parts, but you got to have all of them to create the part the way it needs to be created. So you want to pay careful attention to a couple details. We'll come back to angles and things because now is when the mate process becomes really important. So the interior here is the way that they've set the whole thing up is pretty interesting. So you have the wider base on the bottom. You have these rods on the outside. Then you have just inside of those, the rods going up. And on the inside, you have your top plate. So there's a number of different ways to use mates to line up all these components. And we want to pay attention to each and every one of them. So we're going to go back to our assembly. The ones that you're going to want to make use of are for things like this, cylinders, concentric, and then width mates under the advanced tab wherever possible. So let's start taking a look at those. This is where a lot of this comes in. So you can manually select concentric. We're going to take the long pin, and I'm going to say that and this need to be concentric. And then I'm going to make use of an advanced feature called the width. So you want to grab the inside faces or the outside faces of something, and then the second two are another set of parallel faces. What this does is this creates a mate where you have the width of something evened out between both sides. So you hit OK. I'm going to do the same thing for this. And it's actually going to be, switch back over, do concentric first. Hit the check mark to save it. Then add in the width mate. I'll do the outside just so you can see that that works the same. So the two faces and the two inner faces. And really, really helpful tool for getting things lined up and even. I'm going to do the same thing for these. And some of this is just repetition. Nothing much we can do about it, except we have to establish all of the things. So I can select them in reverse order. That's fine. Now, okay. So these are the shorter pins. Same deal. We're going to set concentric first. Do a width mate. Here we go. Concentric and width. So this, we now need to set up a relationship with this. So we need to do a couple things. When things are floated, you can do what's called a free drag. So I'm going to step out of the mates for a second, just make sure you understand this. Anything that is floated can be free dragged in the environment in any direction. Anything that's fixed cannot. So you want to be very careful about how you orient stuff. We're going to talk about the origin, moving those, center of mass, etc. You can kind of get things in the free drag mode close to positioned where you think they should be, and that will help. So you can get them kind of grossly into position where they need to be. And then, so like this one, I know we're going to need to be there. So there's a couple ways that we can set up the orientation. I'm going to orient these two top and bottom plates to each other first. The simple instinct might be that you want this top face and this top face to be parallel. Okay, great, but you need it the other direction. So you can do what's called flip and do an anti-alignment, which for some things becomes very, very helpful. So now this, I'm going to step out of the mates again for a second to explain. This is still fixed. It's not going anywhere. This can still go somewhere, but we're not rotating it and moving it around in any kind of weird orientation at this point in time. So we're going to get that sort of lined up more or less in place. Make sure to make everybody positively seasick, because that's the best way to do 3D operations. All right. So now we start visualizing how all of our parts are going to come together. So we're going to do the same sorts of things with this one. We're going to do concentric. So it's not going to be that edge. We're going to do concentric. It's going to be looking for cylinder and this side. Don't worry about the orientation yet. We'll get there. So we're going to do another concentric. Okay. Now we're going to do a parallel between this face and this face. And this one, we can move pretty freely. So I'm going to move this a little bit out of our way, trying to keep roughly the same orientation. This one, they mostly constrain these movements in the XYZ plane. You can rotate the components, but we'll specify rotation parameters in a little while. For now, we just want to establish parallel. And if that part were asymmetric and we needed to fix it, we could change it to being anti-parallel. Lots of options and approaches on how we do that. So this one is still floated, but it's fixed sort of within a range of motion. It's going to move with this center rod now, so that whenever I move this, even side to side, they're going to maintain their orientation relative to each other, and they're going to maintain their orientation as far as being parallel to these plates. So you can see we do have a little bit of misalignment here. One of the things you can do is you can add another mate here to say, I want this face and this face to be parallel. That will maintain an orientation, but really the most appropriate way to do this particular mate, to make sure this plate is correctly oriented relative to this one, actually turns out to be another width mate. So this one, I'm going to pick the outside two of these, and I'm going to pick the inside two of these. What that's going to do is that's going to orient this plate such that it's always going to be centered right here. It's always going to be centered in between these. And that's going to help to make things a little more obvious if my view is square. So it'll be centered. So it looks like these long pin and short pin ended up inadvertently with the same dimensions. So we should go fix that real quick, because the long pins and short pins should be different sizes. So we go back to the short pins. And let me edit that base sketch real quick. So remember, we deleted that overall length. So short pin should be 0.27 plus the 0.225 overall. So I'm going to use that inside dimension of 0.27 over 2, verify that it's correct. No, I don't want the center line. I just want the distance here. I'm going to set this as a driving dimension. I'm going to delete this one. I'll set this to be 2.7 over 2, 2.7 over 2. 1.35. Now, when I save that, that's a shortened aspect ratio. And I jump back in. Yes, rebuild with the smaller parts. So I can now find where my two short pins are. So there's my one short pin. There's my long pin. So two of these got reversed. So I'm going to go in and fix that under the mates. Go. This one. Yes, delete that. Move it out of the way. That's the first one I did. So I'm going to edit that. And the cool thing is, with the other relations, I actually can correct this by with the other width instead of going back and redoing everything completely. What I can do is, because I set up a width mate for the other one, I can just switch the two without creating a whole lot of hassle. So that one now is going to end up concentric to this one. And because I've already got the other width mates, I can correct the geometry. That sort of detail becomes important for center of mass later. A whole lot of reasons why. But my two short pins are on top as they ought to be. Two long pins are on bottom as they ought to be. Now, for dealing with these guys, same deal. I'll start with this one. We're going to go concentric here and here. And then we're going to find this face. And we're actually going to do a concentric. Actually, we'll do this first. Concentric with this one. Now, you'll note how everything else moved in conjunction. So with these two in place, I can still move this plate, but now I'm starting to establish that there has to be a certain range of motion. So we'll come back to setting angles here in a few minutes. We need a coincident between this face and this face. So this is now concentric, and we need to double check with our assembly. So this outer one should be in contact with that interface. So we're going to recreate that. So we're going to take this one. We're going to say this one needs to be also concentric to this. And we're going to save that. We're going to say we need a coincident between this face and this face. Actually, I did that opposite. So let me go in and correct that one. I'm going to save this real quick and then show you if you do. So I'll do this as 1B. If you make the terrible life choice of saying, oh, I made a mistake, and you hit Control Z, all of that stuff happens. And you'll notice there's no redo button. So all those relationships we just had are gone forever. If you hit Control Z a couple times, it will undo most of whatever happened, I think, until the last save point. And in some cases, that can be the entirety of your assembly. So that has very much the capability of completely ruining your day. So if instead I close this, importantly, without saving, and then I go, that was dumb. I don't want to do that again. I reopen assembly 1B, and I can continue where I left off. So here, I just have to update that last one I did. Need to edit that feature. Clear selections. I actually need this face and this face to be coincident. And then I need this face and this face to also be coincident. Then I need to add the concentric to this end. Now, when I'm moving this, it maintains a relationship because of how I've specified the details here. So we do the same thing. We continue, rinse and repeat till probably all of you literally get so seasick that you throw up. Concentric, check. Coincident, face, face, check. Concentric, cylinder, check. Actually, face, coincident, face. Then we can do concentric afterwards. You don't have to start with concentric, but sometimes you can cause things to get moved inside of other parts, create all sorts of headache. Concentric. Once you've established the other relations, you don't always have to establish the coincident, for instance, for those faces. You can actually over constrain if you do that, because this can't go side to side. It can do wonky things with angles, but it can't go side to side. So we're going to get that again close-ish to where we want it to be. And now you can see that our range of motion here maintains an orientation that becomes pretty important for getting all of the angles set. So we're going to do the same thing. concentric with this guy. Okay. I'm going to go concentric now with this one. Coincident between this face and that face. Now we need this guy, concentric, this, coincident between face and face. Other end, concentric with the lower pin. And you just systematically work your way through, saving early, saving often. You can't save until you step out. So sometimes it'll ask you to save and update all the parts. Sometimes it won't. Go back in, add some more mates. Okay, concentric there. I'm going to do another concentric here. You could do concentric to the opposite cylinders. You just probably don't want to be in the habit of doing that. So then a coincident. Yeah. Coincident between that face and this one. That gets everything all nice and neatly lined up on the exterior. Now, same deal. Concentric. So this is why assemblies take a lot of time. They can be very time consuming. And especially if you make the horrible, terrible mistake of ever hitting Control Z, you'll wish you hadn't done that. So you want to be very intentional. You want to plan. You want to have a clear idea exactly what you're doing beforehand. And coincident there. Check. All right. So all of our parts are connected and our range of motion is constrained to within this axis. And now what we want to do is we want to say, okay, we need to define the angle to get it to be just what our instructions say. So 36 degrees. And then we'll talk about coordinate system. A lot of stuff today, a lot more luxury than normal, but it's really, 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 really critically important stuff. And you need all of it. So you'll need to go back and probably rewatch several times. That's what a lot of my other sections are doing. So I'm getting a lot of views for just a handful of students, which is good. Okay. Under mates, you can set an angle like so. I'm going to type in 36 degrees. And we're going to say that needs to be the angle between this top face and this face. Problem is, well, that would be called mechanical bind, is what that would be. So that's obviously not quite correct. Let's try the anti-alignment. Not quite. That's still the two plates on top of each other, and that really doesn't. So sometimes you're setting an angle, and you have to do what's called the flip direction here. You have to flip the dimension around to get to 36 degrees for the angle you're actually looking for. Why? Because go back and see geometry and proofs and reference angles and parallelism and all those fun things that probably give a few of you nightmares back when you were wearing headgear as a kid. So you play around with those parameters until you get the correct direction for your particular angle. If you've done all of the other constraints correctly, which we have here, then you've got things set up, and now this won't move. This is now fully constrained. This can move, but that's about it. And really, for the center of mass, this too has to be constrained. So you guessed it, there's going to be one more mate before we can talk about center of mass. And it's going to be a width, because reasons. Makes life easier. Trust me, I'm a doctor. All right. And there it is. Width mate. Now, where is our origin? Now that this is fully constrained, this part still can technically rotate. I'm not going to get into whether or not that matters right now. For center of mass on a centered cylinder, not super important. It's not worth a lot of time to discuss. All right. Origin. It's way over here in the middle of space. Grand. But we need the origin to be here. Well, you'll note something that they have written here, coordinate system 1. It's almost completely implausible to have you guys start bringing stuff in to the actual origin. You can float this and get it close. So you could come in here, you could say float this, and then go, all right, where's that origin again? And then you go and start trying to move stuff around. You got to make the noise, otherwise it just doesn't. It's not the same thing. And you can try and position it, and then you try and figure, okay, I got to get this corner up to that origin. You start trying to fiddle around with it. I'm really close, man. I'm getting there. But realistically, you're going to end up missing by quite a bit, quite often. So instead, because that's going to take 100 million years to get there, and you'll never actually be completely accurate, what you need instead is reference geometry, reference coordinate system, and you need it right here at this vertex. Nope. The actual position needs to be this vertex. And if you've got the vertex already defined as part of the x-axis, blah, 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 you need it at this vertex. It's also important to pay attention to the orientation. Positive x, positive y, positive z. Red is positive x, green is positive y, blue is positive z. So we have z going up, x coming out, y going in. So ours is not quite. So we need to rotate it. You can start by trying to figure out how to get there and kind of rotating and going, you need z to be vertical. You need x to be horizontal. So we're going to go back. We're going to say, I really need not rotating around x. No. I really need this to be 0. And I really need this to be something like 270 degrees almost. And I need that z to be going up. So x is going the right direction now. And to get Z in the up orientation, you have to play around with this occasionally. So this one might need to be 270. So there I've got Z going in the correct direction. Z going in the correct direction, but I need to flip X and Y. So let's go back. Because X needs to be this way. So rotate around. So we actually need to rotate around Z, going the other direction. There we go. We can go minus 90. So now we have positive X, which is red this way, positive Y, which is green going this way, and positive Z, which is up going this way. And this now matches the coordinate system. So now we have coordinate system 1, Z, Y, and X, matching Z, Y, and X for our system. Now we can look at whether or not we have the answer, because it's looking for what is the center of mass for the entire assembly. And drum roll. Mass properties. So center of mass, 75, 93 minus 32.6. And this is very different from what we've got because 73, 93, and 32 are all in MMGS. This is all done in IPS. So we're still using coordinate system 1. The other thing that we have to do is switch from the default to reference coordinate system 1. Then we see minus 1.35. Bring this up alongside just so that we can see it as a reference. There we go. So X is minus 1.35, Y is 3, Z is 3.75. So our answer exactly is B. So there's all these little nitpicky details when it comes to how to get this. And obviously this wasn't a staged answer because you guys watched me go through the entire thing live. It's all about keeping very, very, very careful accounting of all the little details. If you had the X's and Y's switched around, the signs would change for those. So minus 1.35 becomes a plus 1.35. So if you got your coordinate system wrong, you answer C, whoop, wrong, you failed the test. Because that's not the correct center of mass per the coordinate system they gave you. So now that you know all the things and are familiar with a lot more of the mate features, what are some of the questions you guys have? I'll pause the recording here unless we need to add some more in.